There are particles streaming through your body right now. Not just one, not hundreds, trillions, every second. They pass through walls, through planets, through stars, without a sound, no charge, nearly no mass, and until recently almost no trace they were ever here. These are not particles. They are ghosts. And one of them, born in the heart of cosmic violence, just shattered what we thought was possible. Welcome to the mystery of the impossible neutrino. They are the most elusive travelers in the cosmos, whispers of creation itself. They journey across the universe with no baggage, no charge, almost no mass, and hardly a care for the matter they pass through. These are neutrinos, subatomic phantoms born in fire and fury, yet silent as falling ash. To understand neutrinos is to eavesdrop on the universe's most intimate secrets. But these secrets weren't always known. In fact, they began with a mystery. The year was 1930. Physicists studying radioactive decay were stumped. Something was off. Energy was missing. Nuclear decay, especially beta decay, should have balanced neatly. Energy in equals energy out. But it didn't. It was as if the universe had misplaced a tiny fraction of energy every time a neutron turned into a proton. To the physics community, this was a crisis. To Wolfgang Pauli, it was an invitation. At a physics meeting in Tübingen, Germany, Pauli proposed an idea so bold he apologized in advance for even suggesting it. In a now famous letter, he wrote, "I have done a terrible thing. I have postulated a particle that cannot be detected." That terrible thing was the neutrino, little neutral one in Italian, as Enrico Fermi would later name it. A tiny, chargeless particle emitted during radioactive decay that carried away the missing energy. It was an act of theoretical elegance, but it wouldn't be confirmed for another 26 years. In 1956, deep inside a nuclear reactor in South Carolina, physicists Clyde Cowan and Frederick Rines devised a groundbreaking experiment. Using huge tanks of water laced with cadmium chloride, they hoped to catch a ghost. And against all odds, they did. Their detectors recorded the telltale signs of a neutrino, a sudden burst of light from an anti-neutrino-induced reaction. The particle that could not be detected had just been caught in the act. But what exactly had they found? A neutrino is so small and unreactive it can travel through a light year's worth of solid lead and still not interact with a single atom. It's governed not by electromagnetism or the strong nuclear force, two of nature's most dominant players, but by the weak nuclear force. And it's this weakness that makes it so incredibly hard to study. Neutrinos don't scatter, they don't ionize, they don't leave trails, they just go. And they are everywhere, every second. About 100 trillion neutrinos pass through your body. They're coming from the sun, from nuclear reactors, from the Big Bang itself. Most of them are low energy and harmless, relics of more mundane cosmic processes. But some are different. High-energy neutrinos are the cosmic elite. They are forged in the aftermath of supernovae, in the jets of black holes, in the bellies of colliding galaxies. These particles are not merely ghostly, they are mythic. Their energies dwarf anything we can produce on Earth, and if we can catch just one, we can peer into the heart of the most violent events in the universe. But that's the catch, isn't it? Because of their near invisibility, detecting neutrinos requires more than a microscope. It requires ingenuity and scale. Massive detectors are built not to find one neutrino, but to wait patiently as a million fly by in the hopes that one will glance off a proton and leave behind a trace of light. That light is called Cherenkov radiation, a faint blue glow, like a sonic boom of light, produced when a particle moves faster than the speed of light in a medium like water or ice. It's this glow that reveals a neutrino's rare interaction, and it's this technique that would launch an entirely new field of astronomy. In 2011, a facility called IceCube, buried deep beneath the Antarctic ice, detected the first high-energy extraterrestrial neutrinos. It was a revolution. These ghost particles could be traced back to their sources across the cosmos. A new kind of cosmic map had begun, but that map was about to be redrawn again. Because something just happened, something so rare, so energetic, and so utterly unexpected, it has rewritten what we thought we knew about neutrinos. A particle so powerful it eclipsed anything IceCube had ever seen. And it didn't come from the icy depths of Antarctica. It came from the sea, the Mediterranean Sea to be exact, from a detector named KM3NET. A telescope not of mirrors or lenses but of light sensors floating deep below the waves. And in early 2023, this submarine sentinel detected a neutrino with an energy of 220 peta-electronvolts. To understand that number, imagine this. The energy of this neutrino, carried by a subatomic particle smaller than an atom, was greater than the kinetic energy of a fast-pitched baseball. In one particle, invisible, undetectable, until now. This event didn't just break records, it shattered expectations. It's been called impossible, a fluke, a glimpse of something we weren't meant to see. But it's real, it happened, and it's opened a door. To what? We don't yet know. But the journey to find out begins now. If low-energy neutrinos are whispers, then high-energy neutrinos are roars from the distant corners of the cosmos. They don't come from the hum of stars or the warmth of the Earth's core. No, these neutrinos are born in chaos, in places where matter is crushed, flung, shredded, and accelerated to nearly the speed of light. They are the messengers of the universe's most violent events. But there's a problem. They are also exceedingly rare. High-energy neutrinos are elusive even by neutrino standards, while low-energy neutrinos flood us in untold numbers, most from the sun or from nuclear decay. High-energy neutrinos are much more selective. They come from active galactic nuclei, exploding stars, and perhaps even cosmic collisions from the dawn of time. They are few, far between, and almost never interact with anything. And yet, they hold the keys to some of the universe's greatest mysteries. Unlike cosmic rays, which are charged and constantly bent by magnetic fields, high-energy neutrinos travel in straight lines, like perfectly thrown darts across the vastness of space. They don't scatter, they don't slow down, and they don't care about gravity or radiation. That makes them ideal cosmic messengers. Imagine trying to trace a whisper in a hurricane. That's what traditional astronomy does, decoding starlight that's been distorted, scattered, and filtered through billions of light-years of gas and dust. But neutrinos cut through it all. When we detect one, it's like getting a message in a sealed envelope, pure and untouched, from whatever event sent it across the stars. But that's where the challenge lies. To read that message, we first have to catch it. Detecting high-energy neutrinos is like fishing for a single raindrop in the ocean. The odds are absurd. That's why detectors like IceCube in Antarctica were built. A cubic kilometer of ice, yes, a cubic kilometer, buried with sensors to look for the tiny flashes of Cherenkov light when a neutrino finally collides with something. And even with all that ice, years can pass between major detections. But when one does appear, when that single, impossibly energetic neutrino sets off a cascade of light, it can change everything. A single detection can tell us where it came from, how fast it was traveling, and how much energy it carried. From that, we begin to piece together the story of its origin. And what stories they are. Black holes, swallowing stars, galaxies colliding and fusing, supernovae blasting their guts into the void, gamma-ray bursts, spinning like cosmic lighthouses. These aren't just spectacular theories, these are real events, cataclysmic eruptions capable of hurling particles across the universe at unimaginable speeds. But there's more at stake here than just astronomy. High-energy neutrinos are also test pilots for fundamental physics. Their sheer energy allows scientists to study interactions at scales we can't replicate on Earth. They let us probe questions about the structure of space-time, the limits of the standard model, and maybe even the nature of dark matter. Think of high-energy neutrinos as both cosmic detectives and laboratory probes. They're messengers and experiments rolled into one. The quest to find them isn't just about building bigger detectors, it's about knowing where to look. That's why a new era of neutrino astronomy has emerged. Not just passively waiting for neutrinos to pass through a detector, but aiming to catch them, coordinating with other observatories, watching for gravitational waves, gamma-ray bursts, and other signals, using the universe itself as a triangulation system. This approach is known as multi-messenger astronomy, and neutrinos are its quiet MVP. When we detect a high-energy neutrino, we don't stop there. We point radio telescopes, optical scopes, X-ray satellites, all of them, toward where it came from. We cross-check with data from gravitational wave observatories. Was there a merger, a collapse, a flare? Every time we sync these signals, we get a clearer picture of what the universe is really up to. And then came a new challenger. IceCube may have been the giant in the south, but the north was rising. The Mediterranean Sea, deep and dark, became home to a new experiment, KM3NET. Built underwater instead of under ice, it offered a different view of the universe, one that could complement IceCube, and maybe, just maybe, see what others could not. The detectors KM3NET uses are different too. Arrays of optical modules suspended like vertical strings, swaying ever so slightly in the deep-sea currents. Each module waits in perfect silence for a trace of Cherenkov light, for a ghost to tap on the glass. And then, in 2023, one did. An event so energetic, so unexpected, that it shattered the previous record by over 35 times. A neutrino with 220 peta-electronvolts of energy. That's 220 billion electron volts. And it didn't come from a completed detector. It came while KM3NET was still just 10% operational. That one detection wasn't just a success, it was a statement, a message from the universe. You're looking in the right direction, keep going. It redefined what we thought was possible. It validated years of effort from engineers and scientists who believed in the promise of underwater neutrino detection, and it signaled that neutrino astronomy was no longer theoretical. It was here. Now the race is on, to find more of these high-energy neutrinos, to understand where they come from, to unlock the physics they carry, and to open new chapters in the book of the cosmos. Because every high-energy neutrino is more than a particle. It's a story waiting to be told, a whisper from a black hole, a fragment from the Big Bang, a clue in a universe still full of mysteries. And so, the quest continues. Not just in the ice, not just in the sea, but in every dark corner of space, where a whisper might one day become a shout. In the cold darkness of the deep Mediterranean, far below the reach of sunlight or storms, floats a machine so sensitive it can detect a ghost. Not a human ghost, a cosmic one. This is KM3NET, the Cubic Kilometer Neutrino Telescope. A name that sounds like science fiction, and yet it's entirely real. An underwater observatory built not to study whales or shipwrecks, but to listen for the faintest whispers of the universe. Thousands of meters below the surface, off the coasts of Sicily and southern France, a grid of strange, glowing spheres sits suspended in the abyss. Each one is an eye, trained not on the sea, but on what passes through it. They don't blink, they don't sleep, and they're not looking for light from the sun, but for the blue shimmer of a particle born in cosmic fire. To understand why KM3NET is such a marvel, you have to understand what it's trying to do. Catching a neutrino is like trying to capture a single snowflake in a wind tunnel with your hands tied behind your back. They rarely interact with anything, so the only way to detect them is to build something enormous and wait. That's what KM3NET is, a vast three-dimensional net spread out through the sea, filled with thousands of eyes, optical sensors that wait for the light produced when a neutrino finally does the impossible and interacts. When a neutrino slams into a particle of water, It can create a charged particle, like a muon, that moves faster than light travels in water. Not faster than the speed of light in a vacuum, nothing can do that, but faster than light moves through water. And that speed creates a glow, a faint cone of blue light called Cherenkov radiation. Think of it like a sonic boom, but made of light. This is the signal KM3NET is built to detect, and to do that, it uses not one, but two detectors. The first is called ARCA, short for Astroparticle Research with Cosmics in the Abyss. It's based off the coast of Sicily, 3,500 meters underwater, and is designed to detect high-energy cosmic neutrinos, the kind produced by exploding stars, black holes, or colliding galaxies. Arca is tuned for the big ones, the bruisers, the neutrinos with enough energy to light up dozens of sensors as they rip through the ocean like a needle through velvet. The second detector is Orca, Oscillation Research with Cosmics in the Abyss. It's shallower, off the coast of Toulon, France, and focuses on low-energy atmospheric neutrinos. These are the neutrinos that constantly rain down from space, generated when cosmic rays hit the Earth's atmosphere. Orca's job is to study how neutrinos oscillate, a strange property where they shift between different flavors as they move through space. Electron neutrinos can become muon neutrinos, which can become tau neutrinos, and back again. No one fully understands why, but Orca is helping to pull back the curtain. Both Arca and Orca use the same core idea, long strings of spherical modules, each filled with 31 small photomultiplier tubes, or PMTs. These tubes are so sensitive they can detect the faintest flash of light. Together, each of these glass spheres is called a multi-PMT optical module. Imagine a Christmas ornament the size of a beach ball, filled with light sensors, dangling in the dark, listening for a single photon from a passing ghost. Each string of modules rises vertically, like a giant jellyfish, hundreds of meters tall, and the seafloor below is crisscrossed with power cables and data lines, all connected to shore-based control centers. If you saw it from above, it would look like a glowing forest of light, suspended in the blackest waters on Earth. But building it wasn't easy. KM3NET is one of the most ambitious deep-sea science projects ever attempted. Deploying sensors 3 kilometers below the surface requires a level of engineering precision that borders on the impossible. The sensors must survive crushing pressure. They must resist corrosion from salt water, and they must remain perfectly calibrated, even as ocean currents pull and twist at the cables, the anchors, the buoys. To lower them into place, teams use floating cranes and remote-operated submarines. Every module must be carefully positioned, like placing Christmas ornaments on the bottom of the ocean, with robots. One wrong move, one cable out of place, and the whole system could fail. But it didn't. Piece by piece, line by line, the telescope began to take shape. And by 2023, just 10% of Arca was operational. 10%, that's it. And even then, KM3NET made history. It detected something no one expected, a neutrino with 220 peta-electronvolts of energy, a new world record. A signal so strong, it lit up over a third of the detectors in the array, like a flare fired from across the universe. And it did it from the sea, not from space, not from a mountain, but from beneath the waves. This was not an accident. KM3NET was designed for this, built for it. Decades of planning and collaboration from scientists and engineers across Europe, all converging in this one moment. And it worked. Arca saw something IceCube never had, something no telescope had. Not because it was better or bigger or faster, but because it looked at the universe from a different angle. From the northern hemisphere, from the Mediterranean, from deep beneath a sea that had been silent for billions of years. Now it speaks. KM3NET has proven that the ocean can be a window to the stars. That water, when used right, becomes not a barrier, but a lens. And through that lens, we're seeing a new chapter of the universe unfold. Not through visible light, not through sound, but through the faint blue echo of a particle that was never meant to be seen. And this is only the beginning. KM3net is still being built. Arca will grow. ORCA will sharpen its focus. And together, they'll open a new era in particle physics and cosmic discovery. Because sometimes, to hear the universe whisper its deepest secrets, you just have to go deep enough. February 13th, 2023. The Mediterranean Sea, 3,500 meters below the surface. A silence deeper than most humans will ever experience. No sunlight, no sound, no motion, except the gentle sway of a neutrino telescope suspended in the abyss. Then, without warning, a flash. A single neutrino, one tiny particle, traveled across the cosmos and struck a molecule of water near Sicily. And the sea, so quiet for so long, lit up. That moment would become one of the most astonishing detections in the history of particle physics, and the neutrino that triggered it would be remembered by a name only scientists could love. KM3-230213A. Let's break that name down. KM3 for KM3NET. 230213 for the date. 2023, February 13th. And A? Because it was the first major event of its kind recorded that day. But this wasn't just any neutrino. This was a monster. An ultra-high energy neutrino carrying 220 peta-electronvolts of energy. That's 220 billion electron volts, a number so large it's hard to visualize. So here's a comparison. This one particle, smaller than an atom, carried the same kinetic energy as a falling grain of sand. That might not sound like much, but imagine compressing the energy of a sand grain into a subatomic particle, traveling near the speed of light, from an origin that may lie billions of light years away. And it didn't just sneak into KM3net's detectors. It roared. It triggered a cascade of Cherenkov light that set off more than a third of Arca's operational sensors. That's not subtle, that's not noise, that's unmistakable. And here's the wildest part. Arca was only 10% complete. Most of the detector wasn't even installed yet. Out of the planned 345 detection lines, only a fraction were deployed. And yet this incomplete telescope saw what no other experiment had. It broke a record previously held by IceCube, the Antarctic Neutrino Observatory that had detected neutrinos up to around 6 peta-electronvolts. This was not a small step beyond that. It was a 35-fold leap into the unknown. When scientists saw the data, many of them didn't believe it at first. It looked too clean, too strong, too perfect. Paschal Coyle, the KM3net spokesperson, put it bluntly. "My program crashed." That wasn't a joke. The computer analysis system didn't know how to handle the event. The signal was so powerful that it broke through the parameters coded into the software. It wasn't just surprising, it was impossible, at least according to the system's expectations. But it was real. The team ran checks, again and again. They ruled out false positives, bioluminescence, cosmic ray muons, sensor errors, anything that might have produced a similar pattern. And every time the answer came back the same. It was a neutrino, and not just any neutrino, a cosmic one. Its trajectory showed that it had come from outside the atmosphere, a path pointing deep into space, far beyond the influence of the Earth, the Moon, or even our solar system. This was a traveler from somewhere else entirely, but where? That's still a mystery. The team checked maps of known cosmic phenomena. They searched for gamma-ray bursts, active galactic nuclei, blazars, anything that might have spat out a particle with that much power. They even considered cosmogenic sources, ultra-high-energy cosmic rays colliding with the cosmic microwave background. And while there were candidates, none of them lined up with confidence. That might sound frustrating, but in science, mystery is fuel. Because this event did more than break records. It proved something. Something scientists had long suspected, but never seen with such clarity. that the universe is producing neutrinos far more energetic than we thought possible. And they're reaching us, even when our detectors aren't fully built, even when we're not ready. This is like hearing the boom of a volcano on another planet, with a microphone you hadn't finished setting up yet. It validates KM3NET's design, its location, and its mission. It shows that the Mediterranean vantage point offers something new, something IceCube couldn't catch, perhaps due to geography or angle of view, and it sets the stage for a golden age of ultra-high-energy neutrino astronomy. But there's something poetic here, too. The neutrino didn't arrive with fanfare. There was no alert, no flash in the sky, just a silent hit, one line in a data set, one moment of brilliance buried in the darkness of the sea. And yet, that one moment told a story stretching across space and time. Maybe it began near a black hole as matter spiraled into oblivion. Maybe it came from a supernova where a star collapsed under its own weight. Or maybe, just maybe, it came from an ancient interaction between a cosmic ray and the afterglow of the Big Bang. We may never know. But we do know this. KM 3-2-30213A is a landmark, a proof of concept, and a challenge to every assumption we held about the limits of neutrino energy. From here, the scientific floodgates open. How many more are out there waiting to be found? How can we trace them back to their origins? And what will they tell us, not just about the universe, but about the laws of physics themselves? We've caught one. We've proved it can be done, and now we listen. Because the universe is speaking, and thanks to a telescope beneath the sea, we've heard it louder than ever before. At first glance, KM3-230213A might just seem like an exciting win for neutrino astronomy, a lucky catch, an early surprise for a detector still under construction. But as the data rolled in, scientists realized something didn't add up. This wasn't just a rare event, it was an impossible one. At least, according to everything we thought we knew. Let's put this in perspective. The IceCube Neutrino Observatory, our most successful neutrino telescope to date, has been fully operational in Antarctica since 2010. It contains over 5,000 sensors buried across a cubic kilometer of solid ice. For over a decade, it has recorded high-energy cosmic neutrinos from all over the universe. Its highest confirmed detection, roughly 6 peta-electronvolts. Now that's still mind-blowing. A particle carrying more energy than anything we can produce in our most powerful accelerators. But 6 petavolts was the upper limit. After thousands of events and over a decade of data collection, IceCube never saw anything beyond that threshold. And then came KM3-23013A at 220 peta-electronvolts. It didn't just nudge past that ceiling. It obliterated it. More than 35 times the energy of IceCube's record, detected not in a fully optimized observatory, but in a detector that was only 10% built. By every model, every expectation, every probability chart, they should not have seen this, which raised the immediate question, was it even real? Skepticism wasn't just reasonable, it was necessary. The stakes were too high to trust a first glance. Researchers spent weeks running checks. Could it have been a background signal, a misfire from a sensor, a coincidental chain of sensor activity mimicking a real event? But the data held up. The timing was precise. The signal strength matched a high-energy neutrino interaction, and the muon track, long and bright, was consistent with a particle moving straight through the detector at nearly the speed of light. The team compared it to every known phenomenon that could imitate a neutrino: cosmic ray muons, bioluminescent organisms, noise from nearby underwater activity. Nothing matched. It wasn't a ghost, it was real. But how? Why would IceCube, an enormous proven observatory, not see something like this in over a decade, and KM3-net, only 10% complete, catch one so quickly? There are several theories, none confirmed, but each points to a bigger mystery unfolding behind the scenes. One possibility is directional sensitivity. KM3, Net sits in the northern hemisphere, while IceCube is stationed at the South Pole. That gives each observatory a different view of the sky. IceCube looks north, through the Earth. KM3 Net looks south, through the sea. The coverage overlaps somewhat, but there are angles and trajectories only one of them can access at any given time. It's possible that this neutrino, KM323013A, came from a region of the sky that IceCube simply doesn't monitor effectively. If that's true, it means we may be missing entire categories of events just because of where we're looking. Another theory points to detector configuration. KM3 Net's sensors are built in water, not ice, and while both mediums allow for the detection of Cherenkov radiation, they behave differently. Water is clearer in some respects, with less scattering. It may be that certain high-energy events are simply easier to resolve in water than in Antarctic ice. Then there's the energy itself. At 220 peta-electronvolts, this neutrino falls into a theoretical zone that borders on the realm of cosmogenic neutrinos, a class of particles predicted to exist but never before confirmed. These are thought to form when ultra-high-energy cosmic rays collide with the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. If KM3-230213A really is cosmogenic, it's not just rare, it's ancient, a signal from a particle that has been traveling across the universe for billions of years, straight from the earliest chapters of cosmic history. But here's the problem. IceCube has been actively looking for cosmogenic neutrinos for years and hasn't found a single one. So why would KM3NET see one, especially when it's only partially complete? That's the core of the paradox. Either KM3-230213A is something incredibly unusual, or our models of what's usual are simply wrong. Some physicists believe we may be at the beginning of a major revision in our understanding of high-energy neutrino behavior. That maybe there are more of these events out there than we thought. That maybe the universe is producing them more frequently, or that we've underestimated where and how they can be generated. Or, and this is where things get even more speculative, maybe KM3-230213A points to new physics altogether. If you were to stretch the standard model of particle physics to its absolute limits, you'd still struggle to explain an event like this with complete confidence. Some theorists have proposed that such high energies might reveal subtle effects of quantum gravity or even violations of Lorentz invariance, meaning that at extreme energies, the rules of space and time might behave just a little differently. That's the kind of territory we're now stepping into. A single neutrino is pushing the boundary between known science and what comes next. But maybe the most mind-bending part of all is this. There could be many more of these out there. KM3 Net caught one. But it's not even done yet. As the detector grows, its sensitivity will increase, its coverage will expand, and if this impossible neutrino was just the first of many, then the universe is much louder than we ever imagined. It's no longer about whether these events exist. It's about how often, how energetic, and how revealing they truly are. KM3-230213A is impossible only in the sense that it challenges everything we took for granted. But science lives in those challenges, and in every impossibility there is a doorway. So the real question is no longer why this neutrino was so powerful. The real question is, what else is out there waiting to break the rules? Where do monsters like KM3-230213A come from? Not from stars like our sun, not from quiet galaxies or peaceful stretches of space. To create a neutrino with 220 peta-electronvolts of energy, you need a furnace that doesn't just burn, it rages. You need a cosmic powerhouse. These are places in the universe where energy is unleashed on scales beyond anything we can create on Earth, where matter is shredded, crushed, and hurled at nearly the speed of light, where physics is stretched to its breaking point. So where do we start? One of the leading suspects is a class of objects called active galactic nuclei, or AGNs. These aren't just large stars or black holes, they are galaxies whose cores are alive with fury. At the center of an active galactic nucleus lies a supermassive black hole, often millions or billions of times more massive than the Sun. But unlike most black holes, these aren't quietly feeding. They are devouring matter so rapidly that they become lighthouses, blazing with radiation, spewing jets of particles that extend for hundreds of thousands of light years. These jets move at relativistic speeds, close to the speed of light, and they carry enough energy to light up entire regions of space. When one of these jets happens to point in our direction, we give it a different name, a blazar. Blazars are among the brightest and most energetic phenomena in the known universe. They're also top contenders for the origin of high-energy neutrinos. Here's why. Inside those jets, protons are believed to undergo a process called Fermi acceleration. It works like this. Charged particles are trapped between magnetic shock fronts and bounce back and forth, gaining energy each time. Over time, these particles can be accelerated to absurdly high energies, far beyond what our particle colliders can achieve. Eventually, some of those protons collide with photons or other particles, creating cascades of secondary particles, including neutrinos. And if one of those neutrinos happens to be launched in our direction, it travels in a straight line, unaffected by magnetic fields, carrying the full story of its origin right to us. That's the theory, at least. In the case of KM3-230213A, researchers at KM3NET searched the sky for potential sources. They identified 12 known blazars within the uncertainty region of the neutrino's incoming trajectory. That's promising, but here's the catch. None of them stood out. No unusual activity, no flares, no corresponding gamma-ray bursts, just a list of possibilities, which means we're still chasing shadows. So, what else could have created it? Another suspect, supernovae. When a massive star reaches the end of its life, it collapses under its own gravity and detonates in a spectacular explosion, a supernova. These events can outshine entire galaxies for a brief moment in time, releasing enormous amounts of energy into space. In some supernovae, especially those associated with gamma-ray bursts, narrow beams of radiation and particles are launched into space with extreme energy. These could, in theory, accelerate protons through similar shockwave mechanisms, and again produce high-energy neutrinos. But while supernovae are energetic, the very highest energy neutrinos, like KM3-230213A, may require something even more violent. That brings us to tidal disruption events, or TDS. These occur when a star drifts too close to a supermassive black hole. The black hole's gravity pulls the star apart in a process called spaghettification, stretching it into a long, thin stream of matter. Half of that stream spirals into the black hole. The other half is launched outward in a furious jet of debris. The energies involved are staggering. And under the right conditions, TDEs could produce ultra-high-energy neutrinos. But again, we face a familiar problem. No known TDEs were active in the direction KM3-230213A came from. So what does that leave us? It's possible that the source wasn't visible at all, at least not in the traditional sense. Some researchers believe the neutrino may have come from a dark accelerator, a cosmic object that emits particles, but very little electromagnetic radiation. These would be invisible to traditional telescopes, which rely on light, X-rays, or gamma rays to detect distant objects. In other words, there may be entire classes of astrophysical phenomena that we can only detect through neutrinos. That idea is both exhilarating and unsettling. It suggests we've only been looking at a small fraction of the universe, just the parts that shine. But the most violent, most energetic, most extreme events, they might not shine at all. Neutrinos don't care if the event is bright. They don't care if we can see it. They just travel. And by detecting them, we're gaining access to a hidden layer of the cosmos, a shadow world of accelerators, flares, and eruptions that we never knew existed. That's why neutrino astronomy is so revolutionary. It's not just adding new details to the universe we already knew, it's revealing an entirely new map. A map made of energy, direction, and particle identity, not color, not brightness. A map of where space rages, not just where it glows. KM 3-230213A may not have a confirmed source yet, but in trying to find it, we've strengthened the case for a range of exotic possibilities, from distant blazers to dark accelerators, and more importantly, we've proven that something out there has the power to launch a subatomic particle with more energy than any natural or artificial process we've ever observed. That's not just a clue, it's a declaration. Somewhere, something is throwing energy across the cosmos like a cosmic fastball. And thanks to a silent flash deep beneath the Mediterranean, we now know it hit. So we continue to search the skies, not for light but for force, for motion without visibility, and for the cosmic engines that can make the impossible real. If blazars, black holes, and supernovae are today's cosmic powerhouses, then cosmogenic neutrinos are fossils. Not fossils made of stone or bone, but of motion, of collisions so ancient they happened before Earth had cooled, or stars had formed, or galaxies had even taken shape. These neutrinos are echoes of something vast, and some believe KM 3-230213A might be one of them. Let's rewind the universe all the way back. About 13.8 billion years ago, the Big Bang erupted from, well, something we still don't fully understand. But it left behind a permanent signature. A soft, omnipresent glow known as the cosmic microwave background, or CMB. This radiation is the oldest light we can see. Not with our eyes, but with radio telescopes. It's everywhere, uniform and faint, like the residual warmth from a fire that went out billions of years ago. Now, fast forward a few billion years. The universe is forming galaxies. Stars are dying, exploding. And something strange is happening. Particles, protons mostly, are being accelerated to incredible speeds. Speeds so high they become ultra-high energy cosmic rays. These particles are nature's speed demons. They travel across the universe for billions of years, mostly undisturbed, but not entirely, because they collide. Not with planets, not with stars, but with the CMB, the glow left over from the Big Bang. When a high-energy proton hits a CMB photon, something remarkable happens. The collision produces a short-lived particle called a delta baryon, which quickly decays. And among the debris of that decay is a neutrino. This kind of neutrino, born from a collision between the earliest light and the most powerful particles, is what we call a cosmogenic neutrino. It's the ghost of a ghost. A child of violence, yes, but also a child of time. These neutrinos are believed to carry more than 100 peta-electronvolts of energy, making them some of the most powerful particles in existence. And until now, they've remained theoretical. That's why the detection of KM 3-230213A is so electrifying. At 220 peta-electronvolts, it sits well within the predicted energy range of a cosmogenic neutrino. That puts it in rare company. In fact, some scientists believe this might be the first direct evidence that cosmogenic neutrinos exist. Think about that. A particle born not just from a star or a galaxy, but from the structure of the universe itself. From the oldest light colliding with the fastest matter. From a moment that may have taken place billions of years ago in a galaxy we'll never see. The implications are massive. For one, it would confirm long-standing theories about how ultra-high-energy cosmic rays behave and where their energy ultimately ends up. That matters, because those rays are part of the reason our universe is so dynamic. But there's something stranger happening here. Despite years of observation, IceCube has never detected a cosmogenic neutrino, and it's been looking. That's why some physicists are hesitant to immediately label KM 3-23013A as cosmogenic. If these particles are real and detectable, Why hasn't IceCube seen any in over a decade? There are a few possibilities. First, there's sky coverage. KM3NET, based in the Northern Hemisphere, has a different observational window than IceCube, which stares upward from the South Pole. It's possible that KM3NET just happened to be looking in the right direction at the right moment. Second, there's the detection medium. IceCube uses Antarctic ice. KM3NET uses deep seawater. The optical properties of water may offer subtle advantages in resolving certain high-energy events, especially if those events arrive at specific angles. And then there's a third possibility. Maybe these cosmogenic neutrinos are even rarer than we thought. So rare that even 10 years of IceCube data wasn't enough. Or maybe they only come from specific eras in cosmic history, moments when the conditions were just right. That's the haunting part. If KM3-230213A really is a cosmogenic neutrino, then it may have been traveling across space for billions of years, unstoppable, unchanged, unaffected by dust, stars, galaxies, or time itself. It passed through entire clusters of galaxies. It witnessed the formation of worlds. It may have passed directly through planets, stars, and voids, before finally, improbably, slamming into a single molecule of water in the Mediterranean Sea, a particle from near the dawn of time. Landing in our present, that idea reframes everything, because now we're not just detecting cosmic events, we're detecting cosmic memory. Neutrinos, especially cosmogenic ones, may be the only particles in the universe capable of preserving undistorted information from billions of years ago. They carry the signature of ancient physics, of collisions we never saw, of epochs we can barely imagine. And that means they don't just help us study the universe, they help us study how the universe changed, how it aged, how it cooled, how it evolved. In this way, a single neutrino can become a kind of time capsule. And KM3-230213A, if it's truly cosmogenic, it's the first capsule we've ever opened. We don't know exactly where it came from. We may never find the galaxy it originated in, but we do know it exists, and that changes the game. Because now, other neutrino telescopes like IceCube, Baikal GVD, and the upcoming Pacific Ocean Neutrino Experiment will know what to look for, what energy levels to target, what signals might indicate a cosmogenic origin. This is how science advances, not always through proof. Sometimes through provocation. KM3-230213A is that provocation, a challenge to find more, to build better, to go deeper, to listen harder. It's the first whisper of something ancient, the quiet voice of the universe itself saying, "I remember." For most of human history, our knowledge of the universe came from one thing: light. The stars shined, the galaxies glowed, and everything we learned about them came through telescopes capturing visible photons. But light has limits. It scatters, it bends, it can be absorbed, blocked, distorted. And in the most extreme places, the hearts of supernovae, the jets of black holes, the collisions of galaxies, light doesn't always survive. Or worse, it gets scrambled so badly that by the time it reaches us, the story it tells is incomplete. This is where neutrinos come in. Neutrinos are nature's untouched messengers. They move in straight lines across billions of light years, passing through galaxies, stars, and clouds of gas without interacting with anything. They don't scatter, they don't glow. They carry the truth, undistorted and unfiltered. And that truth just got a lot more interesting. The detection of KM3-230213A, an ultra-high-energy neutrino, does more than just break records. It marks a turning point in how we study the cosmos. For one, it gives us direct evidence of a particle traveling across unimaginable distances without losing its identity. It's as if the universe sent us a postcard with no return address, but the stamp tells us everything. This matters because neutrinos can help us solve one of astrophysics' oldest mysteries. Where do cosmic rays come from? For over a century, We've known that the Earth is constantly bombarded by high-energy particles from space. These cosmic rays hit our atmosphere at nearly the speed of light, creating showers of secondary particles, but finding their origin has been nearly impossible. Why? Because cosmic rays are charged, and charged particles are easily bent by magnetic fields. By the time a cosmic ray reaches Earth, it's made so many detours that we have no idea where it started. Neutrinos aren't like that. They are neutral. They travel in perfectly straight lines, which means if you can detect a high-energy neutrino and measure its incoming angle, you can trace it back to its source. That's game-changing. And KM3-230213A proves it's possible at energy levels we once thought unreachable. But there's more. This neutrino's detection also gives us insight into the nature of cosmic accelerators, objects like blazars, gamma-ray bursts, and active galactic nuclei. These are the particle colliders of the universe, environments so intense they can hurl protons, electrons, and neutrinos to energies trillions of times greater than anything humans have ever built. How? We think it comes down to shock waves. When matter is slammed into other matter, like in the jet of a black hole or the shell of a supernova, it creates regions of intense magnetic turbulence. In those regions, particles can be accelerated again and again in a process called Fermi acceleration, bouncing back and forth between magnetic fields until they reach colossal speeds. These interactions produce not just light and gamma rays, but neutrinos as well. And while gamma rays can be scattered or blocked by dust, neutrinos pass through everything. This means that in places where light cannot reach us, neutrinos can. In fact, neutrinos may become our only way to detect what we call dark galaxies, cosmic structures that don't emit light but still affect the universe through gravity, particle emissions, or motion. Some researchers even speculate that there could be galaxies almost entirely made up of dark matter, dark energy, or other exotic particles, detectable only through the neutrinos they shed during violent events. Think about what that means. We could be surrounded by invisible galaxies, hidden from our view, absent from star maps, yet visible through neutrino telescopes like KM3NET. And this event KM3-23013A might be the first direct communication from one of them, but the implications go even deeper. High-energy neutrinos are also becoming essential to the field of multi-messenger astronomy. In the past, astronomers relied solely on light, radio waves, X-rays, and gamma rays to understand the cosmos, but now we've opened the door to multiple messengers: gravitational waves, neutrinos, and electromagnetic signals. By combining data from all these sources, we can get a 3D view of cosmic events. For example, a supernova might produce a burst of gamma rays, a ripple of gravitational waves, and a swarm of neutrinos. Each of these tells a different part of the story, and when we collect all three, we're no longer just observing the universe, we're decoding it. That's what KM3-230213A represents. It's not just a new chapter in astronomy, it's a new language. And as we learn to listen better, to build more sensitive detectors, to coordinate between observatories, to cross-reference particle events with cosmic maps, we'll start seeing things that were always there, but hidden. Hidden in the chaos of the early universe. Hidden behind black holes, hidden behind clouds of gas, or even behind the glare of our own galaxy. The violent side of the cosmos is no longer out of reach. We're now exploring a layer of reality where explosions happen in silence, where messengers don't flash or burn but glide, where the universe doesn't scream but whispers. And for those who know how to listen, the message is clear. There is more energy, more violence, more truth, waiting to be found. KM3-2300213A is just the beginning. And with every high-energy neutrino that follows, we are sketching a new map of the universe. One that is not made of light, but of motion. Not all discoveries push us to look outward. Some force us to turn inward, deep into the fabric of matter itself. KM3-230213A is more than a clue about the violent universe. It's also a stress test for the laws that govern everything we know. A particle so small, so elusive, and yet so energetic, it may be cracking open the door to a new kind of physics. Let's start with the basics. In particle physics, we have a framework called the Standard Model. It's a mathematical blueprint that describes the behavior of all known particles and forces, except gravity. It includes electrons, quarks, photons, gluons, and yes, neutrinos. According to the Standard Model, neutrinos should be massless. But experiments have proven otherwise. Neutrinos have mass. Tiny, yes, millions of times smaller than an electron, but still not zero. That discovery alone shook the foundations of the model. Because if neutrinos have mass, then either the Standard Model is incomplete, or we're missing a piece of the puzzle entirely. KM3-230213A adds fuel to that fire. At 220 peta-electronvolts, this single neutrino carried more energy than any we've ever detected. And when particles reach extreme energies, strange things can start to happen. Theorists believe that ultra-high energy neutrinos like this could help test the limits of quantum field theory, the very framework that underpins the Standard Model. For example, at these energy scales, physicists can study whether neutrinos still obey their expected oscillation behavior, the phenomenon where neutrinos change flavors as they travel. Normally, a neutrino born as an electron neutrino can morph into a muon or tau neutrino, and vice versa. This process is well documented at low and medium energies. But at ultra-high energies, we're in uncharted territory. What if oscillation breaks down? What if new behaviors emerge? That would imply that quantum decoherence, essentially the breakdown of predictable quantum behavior, might be setting in. And some physicists believe that decoherence could be a faint whisper from something even more exotic: quantum gravity. Gravity, as we know, is the one force the Standard Model cannot explain at the quantum level. It's governed by general relativity, a completely separate framework. Merging quantum mechanics and gravity into a unified theory has been one of science's great unsolved goals for nearly a century. But it's possible that ultra-high energy neutrinos like KM3-230213A might feel tiny fluctuations in space-time caused by quantum gravity. And if we can detect those fluctuations in how the neutrino behaves, scatters, or oscillates, we might get our first clues about the long-sought theory of everything. Some proposals suggest that at extreme energies, the fabric of space-time becomes foamy, not smooth but jittery at microscopic scales. Neutrinos traveling across billions of light-years might accumulate subtle effects from this foam, which we could potentially measure in their arrival times or flavor ratios. So a neutrino like KM3-230213A isn't just telling us where it came from. It might be telling us what space itself is, and that's not the only mystery it touches. There's also the question of neutrino identity. Right now, we classify neutrinos as Dirac particles, meaning they are distinct from their antiparticles. But there's another possibility, that neutrinos might be Majorana particles, particles that are their own antiparticles. If that's true, it could explain one of the biggest cosmic riddles. Why is the universe made of matter and not antimatter? In the early universe, matter and antimatter should have existed in equal amounts, but if neutrinos are Majorana particles, they might have allowed for a process called leptogenesis, which tilted the scales just enough to leave behind a universe made of matter, of galaxies, planets, people. In this way, high-energy neutrinos might not just be silent travelers from the past. They could be the reason we exist at all. And let's not forget one last implication, one that creeps in at the edge of speculation. If KM3-230213A didn't come from a known astrophysical source, if it wasn't from a blazar, a gamma-ray burst, or a cosmogenic collision, then what created it? Some have proposed even stranger possibilities. Could it be evidence of a top-down decay, a relic particle from the early universe finally breaking down after billions of years, releasing an ultra-energetic neutrino in the process? Could it be a sign of exotic dark matter interactions, or of physics that violates Lorentz invariance, the bedrock assumption that the laws of physics are the same everywhere in the universe?
Each of these possibilities stretches the boundaries of known science.
But that's what makes KM 3-230213A so important. Because science only grows when something doesn't fit. When a particle appears with more energy than expected from a place we can't identify, displaying behavior we didn't predict. That's when things get exciting. We're not just refining models, we're poking at the seams of reality. And we're doing it not with billion-dollar colliders, but with a neutrino, a tiny, neutral particle that traveled across the universe without ever blinking, until it collided with a molecule of water under the sea. KM 3-230213A may one day be looked back on as a first marker, the particle that began a new era in both astronomy and physics. A moment when the sky didn't just tell us where things are, but what things are. Long before KM 3-230213A lit up the sea, long before neutrino astronomy became real, there was a challenge. How do you build a telescope for something you can't see? A detector for a particle that almost never interacts? And how do you do it not in space or on land, but 3 kilometers under the sea? Welcome to KM3NET. At its core, KM3NET is an engineering story, a tale of design, precision, and audacity. Because what the KM3NET team built wasn't just a scientific instrument, it was an entirely new kind of observatory, a telescope made of darkness, suspended in one of the most extreme environments on Earth. Let's start with the basics. KM3NET isn't a single detector. It's two separate but interconnected arrays, Orca and Arca. ORCA, located off the coast of Toulon, France, focuses on lower energy neutrinos and studies how they oscillate between flavors. Arca, off the coast of Sicily, goes after the big game, high-energy cosmic neutrinos from deep space like KM 3-230213A. But the concept is the same. Use water as a detection medium and search for the blue light created when a neutrino finally, miraculously, interacts. That light is called Cherenkov radiation. When a charged particle, like a muon produced by a neutrino interaction, moves faster than light can travel through water, it leaves behind a cone of faint blue light. And that cone is the only trace a neutrino leaves behind. So KM3NET's job is to catch that cone. How? With thousands of spherical optical modules, clear glass spheres, each the size of a beach ball. Inside each sphere, 31 photomultiplier tubes, or PMTs, sensitive light detectors that can catch even a single photon. These are known as multi-PMT optical modules. Unlike earlier designs that used one large sensor per sphere, KM3NET's modular approach increases angular resolution, improves background discrimination, and boosts the odds of detecting faint signals. Each sphere is a high-tech eye, and KM3NET has thousands of them, but they don't just sit on the seafloor. They float in vertical strings suspended by buoyant cables anchored to the seabed. Each string can rise hundreds of meters, holding dozens of modules at regular intervals. And it's not just a few strings. Once completed, KM3NET will have over 300 detection units like this across both sites. Together, they form a three-dimensional lattice of eyes in the deep. A volume telescope, not one that points in a single direction, but one that listens to everything. But building this wasn't easy, not even close. Deploying electronics in 3,500 meters of salt water is a nightmare. The pressure is immense, 350 times what we experience at the surface. Salt corrodes everything. Cables twist, currents shift. The water is dark and cold and unforgiving. To make this work, engineers had to rethink nearly every part of the system. First, the deployment process. Each detection string is coiled into a compact unit, like a high-tech fishing reel, before being lowered to the seabed using specialized floating cranes. Once on the ocean floor, the unit is triggered to unfold, allowing the cable to rise vertically while modules self-align. It's delicate work. Precision matters. If a string rises at the wrong angle, or if a module fails to calibrate, it could blind a section of the detector. So every sensor includes onboard systems for self-monitoring, time synchronization, and calibration. Time synchronization in particular is critical. A Cherenkov light cone may pass through the detector in nanoseconds. To reconstruct the direction and energy of the neutrino that created it, every module must know the exact time each photon was detected, to within a billionth of a second. That level of precision is staggering, and yet it works. Each module is connected via fiber optic cables that run along the seabed to shore stations in France and Italy. There, massive servers handle real-time data processing, event triggering, and long-term storage, and it's not just neutrinos they watch for. These modules also help monitor the deep-sea environment. They measure salinity, temperature, ocean currents, and even bioluminescence. This data is invaluable not just for calibration, but for Earth and sea sciences, offering one of the most advanced long-term underwater observation systems on the planet. All of this, every sensor, every string, every software update, had to work together for one reason: to catch the uncatchable. And then in February 2023, it did. With just 10% of Arca complete, KM3-Net detected the most energetic neutrino ever recorded, KM3231213A. Over a third of the deployed sensors lit up, the time sequences aligned perfectly, the muon track was reconstructed in 3D, the energy calculated, the event verified. This was not a test. This was the system doing exactly what it was built to do, even before it was finished. It's a testament to engineering vision, to the scientists and technicians who believed that an underwater neutrino telescope wasn't just possible, it was necessary. And this is just the beginning. KM3-Net is still growing. By 2029, both ARCA and ORCA will be fully operational. And with other observatories, like IceCube Gen 2, Hyper Kamiokande in Japan, and the Pacific Ocean Neutrino Experiment joining the global network, we're entering a new age of neutrino detection on a planetary scale. The oceans, the ice, the Earth itself is becoming an instrument. Because to understand the deepest truths of the cosmos, we don't just need bigger telescopes. We need new kinds of telescopes, ones that can see without light, ones that can hear the silence, and sometimes to build those, you have to go where no one's ever looked before, deep under the sea. February 13th, 2023 was not the end of a story. It was a beginning. The moment KM3-230213A lit up the Mediterranean Sea, a signal was also lit across the scientific world. The age of neutrino astronomy had arrived. But this isn't like the astronomy you're used to. There are no mirrors, no glass lenses, no cameras capturing visible light. This is a new kind of listening, a way to study the universe through particles, not photons. And now the question is no longer if it works. The question is, what's next? The answer begins with one word: scale. KM3-Net is still under construction. Only a fraction of its sensors are in place, and yet, even in this unfinished state, it detected a neutrino more powerful than anything we've ever seen. So what happens when it's complete? By 2029, the full array, ARCA and ORCA together, will be operational. That means thousands more optical modules covering a vast volume of deep-sea water will be listening for signals from across the cosmos. But KM3-NET won't be alone. Around the world, other next-generation neutrino observatories are rising. At the South Pole, IceCube Gen 2 is under development. It will expand IceCube's original detector by a factor of 8, pushing deeper into the Antarctic ice and sharpening its ability to catch rare, high-energy neutrinos. In Japan, Hyperkamiokande is taking shape, an enormous underground water detector designed to study neutrinos from both cosmic and terrestrial sources, with unprecedented precision. In the Pacific Ocean, a project called P1, the Pacific Ocean Neutrino Experiment, aims to place neutrino sensors deep beneath the waters off British Columbia, adding yet another eye to this growing global network. These aren't just isolated experiments, they're becoming a web, a planet-wide sensor grid capable of watching the sky in a way no single telescope ever could. And they won't work alone. They'll be linked to gravitational wave observatories like LIGO, VIRGO, and KAGRA, which listen for ripples in space-time from colliding neutron stars and black holes. They'll sync with gamma-ray satellites, X-ray telescopes, radio arrays, and optical surveys, each catching different pieces of the puzzle. This is multi-messenger astronomy taken to the next level. A burst of gamma rays might be matched with a gravitational wave. A spike in neutrinos could point to the same sky region. Together, they form a complete timeline of a single cosmic event. Imagine this: a massive star collapses into a black hole. Gravitational waves ripple out. High-energy neutrinos burst into space. Gamma rays flash, and telescopes on Earth and in orbit catch the optical afterglow. Each signal arrives at a different time. Each tells a different part of the story. And together, they allow us to reconstruct the event, second by second, from deep space.
That's not science fiction. That's the future.
But even more exciting is the unexpected. Right now, we have theories about where neutrinos come from: blazars, supernovae, gamma-ray bursts, tidal disruption events. But these are guesses, educated ones, but guesses all the same. The next generation of detectors might reveal entirely new phenomena, sources we've never considered. Dark accelerators, exotic remnants of the Big Bang, collisions in regions of space hidden from light, visible only through the faint tap of a neutrino arriving on Earth. And beyond that lies something even more profound. As we catch more high-energy neutrinos, we'll begin to probe the structure of space-time itself. We'll test how neutrinos behave at extreme energies. We'll study how they change flavors over vast distances. We might even detect subtle distortions caused by quantum gravity, tiny fingerprints of the unification between Einstein's general relativity and quantum mechanics. These detectors become not just observatories, but laboratories for fundamental physics. You're not just looking for stars, you're testing the laws of reality. But progress won't come from sensors alone, and it will come from collaboration. The future of neutrino astronomy is global. Scientists from dozens of countries, many of whom used to compete, are now working together, sharing data, standardizing systems, creating networks that cross borders, languages, and oceans. This kind of cooperation doesn't just benefit science, it sets a template for something even bigger: a unified search for truth. Because neutrinos don't care where you're from. They don't stop at national boundaries. They arrive from the depths of space and land on all of us. And if we want to hear them clearly, we have to listen together. This is the next chapter, not just building telescopes, but building unity between institutions, between nations, and between scientific disciplines. KM3Net started as a dream, an underwater telescope for invisible particles. It is now a pioneer. And soon, it will be part of something much greater, a worldwide network of detectors forming a shell around the planet, tuned not to light, but to truth. Truth in the form of silent particles, born in fire and launched across space. Truth that arrives without warning. Truth that can't be hidden, only heard. And for the first time in human history, we're learning how to hear it. Catching a neutrino is hard. Catching one under 3,000 meters of salt water? That's not just science, that's defiance. The KM3NET experiment has captured the world's most energetic neutrino to date. But what most people don't see, what no scientific paper fully conveys, is just how many things had to go right. in one of the most hostile environments on Earth. Deep-sea neutrino detection isn't just difficult, it's a logistical and engineering nightmare. Let's start with the obvious: pressure. At 3,500 meters below the surface, the pressure is over 350 times atmospheric. Every square centimeter of every sensor is being squeezed. Electronics, glass spheres, cables, they all have to survive this crushing force for years. Any structural weakness, any microfracture in a glass housing, any failed seal means catastrophic failure. The module implodes, the data is lost, the system is compromised. Now add corrosion. Salt water is unforgiving. It eats away at metal, it seeps into joints, it erodes seals, peels insulation, and accelerates aging in even the most rugged materials. Every sensor, anchor, and cable on KM3NET has to be designed to survive not months, but decades of continuous exposure to salt and pressure. Next, consider installation. These detection modules aren't just dropped into the sea, they're deployed with floating cranes and specialized robotic systems, carefully lowered to the ocean floor with pinpoint precision. Each line of sensors must then unfurl vertically, hundreds of meters tall, without tangling, breaking, or drifting off course in underwater currents. And speaking of currents, the ocean moves. Even at the bottom, there are slow, powerful flows that shift with seasons, storms, and tectonic activity. KM3NET's vertical strings must remain perfectly aligned, with each optical module in the right position, at the right angle, constantly recalibrated to maintain accuracy. Then there's the matter of light pollution, but not from cities or satellites. Underwater, the sea is never truly silent. Tiny organisms, plankton, jellyfish, deep-sea shrimp, emit bioluminescent flashes. These natural light sources can trigger false positives in the sensors, so the system has to be smart. It must distinguish between a random flash from a glowing copepod and the faint cone of Cherenkov radiation from a cosmic neutrino born near a black hole. That means real-time data filtering, background rejection, and self-diagnosing calibration routines, all running autonomously 24/7 in the dark. But technical challenges are only half the story. KM3 NET is an international collaboration stretching across countries, languages, and laws. With sensors off the coasts of France and Italy, the project relies on partnerships with local governments, maritime authorities, academic institutions, and European funding bodies. Every deployment has to be approved, timed, and executed within tight regulatory windows. Weather delays can throw schedules off for months. Equipment failure can mean waiting until the next calm season. Because working on the ocean floor is not like repairing a telescope on land. It requires coordination between research ships, divers, submersibles, and deep-sea robotics. And then there's politics. In the race to build neutrino detectors, not every country plays nice. Russia, for example, has long been involved in deep lake neutrino detection through the Baikal GVD project located in Lake Baikal, Siberia. Originally, Baikal GVD and KM3NET shared data and insight. But as geopolitical tensions escalated in recent years, that cooperation fractured. As of now, collaboration between KM3NET and Russian teams is limited or non-existent. That means less global coordination, less cross-validation, and duplicated efforts instead of unified discovery. Science may be universal, but the world isn't always aligned. Then there are the environmental responsibilities. Installing thousands of sensors in pristine marine ecosystems comes with an ethical burden. KM3NET can't simply plunge its systems into the ocean without asking questions. Will the anchors damage coral or sediment beds? Will sensor cables disrupt migratory paths of fish or marine mammals? How will the light emissions affect deep-sea life? That's why KM3NET also functions as a deep-sea observatory, not just for neutrinos but for marine biology, oceanography, and geophysics. It tracks temperature, salinity, and seismic activity. It monitors ecosystems. It listens for whales. It's not just looking at the cosmos, it's watching the Earth too. In doing so, KM3NET becomes more than a telescope. It becomes a model for how future scientific instruments can serve dual purposes, exploring the unknown while protecting the known. And despite all these challenges, it works. Somehow, through salt and pressure, politics and plankton, bureaucracy and biology, KM3NET succeeded in detecting the most energetic neutrino ever observed, with only a fraction of its infrastructure operational. With just a sliver of its sensors online, it caught the impossible. That's not just engineering excellence, that's resilience. Because the deeper lesson of KM3NET is this: to hear the quietest voice in the universe, you need more than technology. You need patience. You need partnership. You need to fight against the current, literally and metaphorically, every single day. And when you do, the universe speaks. When we talk about KM3NET, we talk about neutrinos. We talk about 220 peta-electronvolts, about Cherenkov light in salt water, about violent galaxies and billion-year journeys. But quietly, steadily, something else is happening. This telescope beneath the sea is reshaping more than just science. It's reshaping our relationship with the planet, our sense of global purpose, and our understanding of how science serves humanity. Because KM3NET doesn't just peer into the cosmos, it listens to Earth. Let's start with the sea itself. To build a neutrino detector 3 kilometers underwater, scientists had to confront the reality of the ocean, not just as a medium, but as a living system, a place with currents, chemistry, and life. So they began embedding sensors, ones that could measure temperature, salinity, pressure, and underwater noise. They added instruments to monitor deep-sea ecosystems, to study bioluminescence, and to track natural seismic events. What they ended up building was not just a particle detector, they built a marine observatory. Today, KM3NET is one of the most advanced long-term monitoring systems in the deep sea. It provides real-time environmental data to climate scientists, marine biologists, and geophysicists. It tracks rising ocean temperatures. It helps detect undersea earthquakes. It listens for migrating whales and watches for patterns in plankton blooms. It even studies the long-term health of the Mediterranean, one of Earth's most historically significant and ecologically vulnerable bodies of water. In an era of climate crisis and ecological uncertainty, this data is not just valuable, it's essential. KM3NET reminds us that the frontier of discovery isn't just out there in space. It's down here beneath our waves. And that sense of dual purpose, of looking outward while caring inward, carries over into education. Because a project like KM3NET doesn't just inspire scientists, it inspires students. The idea that somewhere in the pitch-black abyss of the ocean, a telescope is catching messengers from the edge of the universe. That's the kind of idea that wakes something up in young minds. Across Europe, and increasingly across the world, KM3NET has become a symbol of science in action, a living classroom for physics, oceanography, engineering, and environmental stewardship. Schools partner with the experiment. University students help develop calibration software, data models, and simulation tools. Postdocs travel to deployment sites and work aboard research vessels, learning not just theory, but how science works in the real world. And when KM3-230213A was detected, it wasn't just an academic victory. It was a moment of belonging for everyone who had ever touched the project. From interns and engineers to students and support staff, everyone could say, I was part of that. That feeling of shared discovery is what fuels science at its best, and that brings us to something deeper, more fragile, more rare: international cooperation. KM3NET involves scientists, technicians, and engineers from more than a dozen countries: France, Italy, the Netherlands, Germany, Greece, Spain, Croatia, and more. Different languages, different funding systems, different ways of working, and yet, one goal: to build something that no one country could build alone. This collaboration stretches across politics and generations. It survived funding delays, engineering setbacks, and even global disruptions like the COVID-19 pandemic. And it continues today, expanding, improving, evolving. This matters because in a world where headlines often highlight division, KM3 NEAT is a quiet, persistent example of what humans can achieve together. It doesn't broadcast nationalism, it doesn't plant a flag. It just listens to the sea and to the stars, and when it hears something extraordinary, it tells everyone. That openness is rare, and it's vital, because neutrinos don't belong to one country. They don't speak one language, they don't orbit political lines, they arrive silently and land everywhere, so our response must be just as borderless, just as unified. And finally, there's this. Projects like KM3NET don't just change what we know, they change who we become. They teach us to think big, to build things that last, to ask questions that may take decades to answer, and to understand that some of the most powerful messages in the universe arrive without sound. That sometimes the most meaningful discoveries are not explosions of light, but patterns in the dark. KM 3-2302138 wasn't just a triumph of physics, it was proof that if we build something carefully, patiently, and together, we can catch a particle that traveled for 1 billion years, using nothing but water, light, and belief. That is the broader impact, not just science, but hope. A single particle, smaller than an atom, moving near the speed of light, carrying more energy than anything ever recorded of its kind. And it didn't make a sound. It simply arrived. KM 3-2302138 wasn't a light in the sky. It wasn't something you could see through a telescope or hear with a radio dish. It was a ghost, a traveler, a cosmic messenger that slipped through planets, stars, and galaxies for possibly billions of years, only to collide with a single molecule of water beneath the Mediterranean Sea. And in that moment, a signal, a flash, history. But this is not just a story about a neutrino, it's a story about how we listen. For most of our existence, we've watched the universe through light. We built glass lenses, mirrors, and satellites. We watched stars flicker and galaxies dance. We followed the light. But the universe is more than light. It whispers in gravity. It echoes in neutrinos. And sometimes the loudest messages are hidden in silence. KM3NET cracked that silence open. With thousands of sensors dangling in darkness, beneath crushing pressure and salt and current, it became something more than a detector. It became a window, not to what is bright, but to what is true. The neutrino it captured didn't just come from somewhere far away. It came from something powerful, something unknown, something that for now we can only imagine. It may have been a blazar, a gamma-ray burst, or the ghost of a cosmic ray smashing into the afterglow of the Big Bang. Or it may have come from something we haven't yet conceived. A dark accelerator, a decaying relic of early creation, or a crack in physics itself. And that's the point. We don't know, not yet. But science begins with not knowing. It begins in wonder, in uncertainty, in curiosity. It begins with one impossible event, and the question that follows, what else is out there? KM 3-2302138 reminds us that we're just getting started. That even now, after centuries of astronomy, physics, and exploration, there are messages arriving from the universe that we've never heard before. And they're getting through. They're slipping past the noise, past the filters, past our assumptions, and into our understanding. Neutrinos, once called impossible to detect, are now showing us new maps of reality. Maps not drawn in color or starlight, but in motion, in timing, in energy. And they are showing us more than galaxies. They're showing us ourselves. Because in this story, we're not just observers, we're part of the system. We built the detectors, we asked the questions, we chose to believe that even the faintest whisper from across the universe was worth catching. And when we did, the universe answered. That is the legacy of KM3NT, not just a world record, not just a scientific milestone, but a signal that we are ready for more questions, more mystery, more wonder. We are building telescopes in the sea, in the ice, in the mountains. We are linking detectors across hemispheres and disciplines. We are listening for lightless things and finding them. In the end, this story is about connection. A neutrino that began its journey before our planet had pyramids, reached a detector that wasn't even fully built, and told us that the universe is louder, wilder, and more surprising than we dared to hope. This is what it means to explore, to ask questions that take decades to answer, to build instruments that may only detect one thing, but that one thing changes everything. KM3-230213A will not be the last. Others will come, some even stranger, some even more powerful. And with every one we detect, our map of the universe will grow. Not with stars, but with truth. The universe doesn't send answers. It sends messengers, and we're finally learning how to read them. So here we are, standing on the shore of the cosmic ocean, lowering our ears into the sea and hearing, for the first time, the sound of the impossible. This is not the end. This ... is the frontier. Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.